Now let's look at the next tool on our list. The next tool on our list is a right-handed, and this is the MVJN is a standard for different orientations of lathe tools. So let's go take a look at a chart that shows what those are. But it's okay. Here's some standard ISO profile tools. It's International Standards Organization. And when this was developed, the tools were permanent. You'd had a permanent tip that's brazed onto a shank. Okay. Technology's changed, but we've taken the same nomenclature and profiles off here. The negative rate indexable toolbar. Okay, and so this is the part number, and this is actually for the insert. And then this is for the turning tool itself. So let's go to the turning tool, and it's a faster little hop to what the catalog looks like. And let's look at the catalog. Okay, up here in the top shows all the different shapes for these standard cutters. And so what we have is this is a one with a round insert to make profiles. This one only cuts on the face with a square diamond shaped insert. Here's the same insert but at a slight angle. Here's one going in 90 degrees. And then we're putting in the tool description. Put in our tool description from our spreadsheet. Okay, it's tool number 3. We use flood coolant, it's carbide material. Offset number 3. We're going to put in our description. We're going to move off. We're going to trim this down. So it's a right-handed MVJN. We're just going to put indexable turning tool holder. We're going to say tool, so tool holder. Vendor is Hurdle, but our insert is a different brand. The hurdles weren't available. So let's put the product ID of our tool holder. We're going to call this the OD tool. OD turning tool. We're going to go to insert, and we should be able to plug in the letters and get most of this. So we are using this VNMG 332 general purpose insert. So it has a it's a diamond shaped at 35 degrees. The type is general purpose. So it's a VNMG insert with a 3/8 inscribed circle with a 1/32 nose radius and a thickness 3/16. So that gives us a VNMG 332 insert, which is what we have here, 332. They drop the zeros. So it should have 2 cutting edges here. It can be flipped this way and rotated 180 degrees for 2 more edges on the opposite side of the insert. Okay, we're going to go on to the next. Our holder. We're using a multi-lock. Starts with an M. Okay, and it should be it's an MVJN holder. So we want that to check to match. So right now we got MVL. We're going to change L to J. Gives it -3 degrees of angle, lead-in angle. And N was the last letter, and it's right-handed side. So that's what the R stands for. Okay, so now we're going to go and put in our dimensions here. So we need to go back to our specs here. So let's start with our overall length. So our overall length is 5 inches. So we're going to put in 5 there. And our shank height is 1 inch. And our shank height is also 1 inch. Shank width. Okay. Now the head length, it is 1.66, and the back of the bar of the cutting edge is 1.25 inches. So we're going to put in the head length of 1.66 and a cutting width 1.25. And that should look, in general, pretty close to what our holder is going to look like. I'm going to leave the chamfer width and chamfer heights alone. I'll go to setup. It's pointing the correct direction. It's going to be facing the spindle. Okay. And compensation is going to be tip tangent. And on feeds and speeds, we're going to select constant surface speed, and so that'll change the RPM of the lathe, and our largest diameter is going to be 2 inches. Okay, we're going to set a constant surface speed of 500 feet per minute, which is moving along pretty well, and so that means that the stock diameter of 2 inches, which is our maximum part size, will have a spindle speed of almost 1,000 RPM. But as it goes closer and closer to the center, it's going to increase that RPM to keep the constant 500 feet per minute with this cutter. And we'll see how that goes. And then we're going to hit OK. So we've just created tool number 3. Now we're going to use this tool in a couple other capacities. So we're going to be able to copy this tool to make up a couple other tools, so we'll move along a little faster. And then we're going to do the same thing with our drill bit. We're going to just keep copying that tool, and it'll keep its information. We'll change the stuff that's different. Okay, so now let's take a look at some examples of fixed lathe tools like this one. Okay, here we have an example of several types of tools. Most of them are outside diameter tools. As you can see in the image on the far right, you can see the same tool we've just spec'd out for our S60 program. They're using a different tool, which is stouter. It uses a square shape insert. And they're using that to rough away the material before the tool we chose comes in and cuts the rest of the part to finish size. So it's doing a facing operation, and now it's going around to the outside edge and doing an operation on the outside diameter. So this would be considered a radial tool because it faces the radius of this cut. Now you'll notice, you might have heard the RPM changing pitch as the cutting goes, and that's because the RPM of the machine is changing speed based off the diameter that the cutter's cutting, so that the surface finish footage is the same. You get a consistent finish no matter what diameter. Here we're seeing the part come to shape. The front has a full radius on it, so it's roughing the radius. Now it's switching to the tool that we specified that we're using. It's not facing the direction, it's facing the opposite way from our viewing screen. So it's coming in and it's doing a secondary roughing with this smaller tool. The diamond shape's great because it can get a variety of angles, and it has a very small nose radius. Okay, we now switch tools to the same cutter. It's different handedness. I believe the spindle has changed directions. And now we're cutting it down to finished size. We're moving on to tool number 4. Tool number 4 is a grooving tool. It's an outside diameter grooving tool. So OD grooving tool. We're going to copy that description, and we're going to create a new turning tool. And under general, our description is going to be OD grooving tool. We go back to our spreadsheet, and the vendor is Turing, and we're going to go to we're going to go ahead and go to MSC and see what we selected there. So it's a solid grooving tool. It's like a boring bar, and we're going to use this on the outside diameter to make the 1mm slots on the outside, I believe. So let's go down to the specs. We should have all the specs here. And we got our overall length. This tool is metric, so all the numbers are going to be in metric. Fusion is tool number 4, flood, carbide, and so it's a 1mm grooving tool. And the vendor was Turing. So we'll copy that. ID from the description here. Put it in here so there's no question if we need to come back and change what that is. Okay. Tool type is a grooving tool, and we have a square tip. We're not really using an insert, so we are going to use it as an inch tool. What we'll be able to do is you can type in 1 mm, and it'll calculate the decimal equivalent for us because our program's going to be in English. So it's a 1mm width, and the corner radius is uncoded. It doesn't say, it must be sharp. It doesn't have a radius on it. So we're going to say that the corner radius is 0. See if it'll accept that. The width on the groove is 1mm. And our maximum depth, not really sure what to put there. The tool, we'd have to look at their tool catalog. It's not giving us enough information here. But for the purpose of what we're doing with this tool, we're only going 1mm deep. So we're going to put our overall length as, let's put 4mm. And then a head length of 4mm. And we'll go ahead and put the thickness at 1mm. Okay, we're going to go to the holder. There really isn't a holder, but it's the body. It has a round shank. And it's grooving type. We're doing external grooving. Okay, and our overall length was, I believe, 30 millimeters. Shank diameter, or shank diameter is only 4 millimeters. It's kind of out of scale here. So the shank width is 4 millimeters. And then our head length is 12 millimeters. So we're not really using an insert, but we've modeled something that's close to the size of it. The critical thing is the millimeter width here. Okay, we're going to go to setup, and this is actually going to face, as we see it here, at 0 degrees orientation to the spindle. Feeds and speeds, I think we're just going to leave this at default. We're going to go to constant surface feed at 2 inches. And we're going to say 200 feet per minute, or 250. Okay, and we're going to select OK. So now we got our OD grooving tool. We expand this out, we can see our full dimension. All right, we're on number 4. Okay, so let's go back to our list and see what tool 5 is. Okay, so this tool is a boring bar. I believe it's also a solid cutter. It's not using an insert. Let's go look at what it does. So it's going to be our first tool, lathe tool we're going to do axial moves with though. So it's a very small boring bar. Okay, if we look at our specs, if we were to look back at our turret, it's going to face forward like a drill bit. But you go in with a drill first, and then you take the boring bar and make the holes bigger. This, we're creating a new turning tool. The general type. Okay, so it's going to be number 5, number 5. We're making a boring tool. Okay. We're going to go back to our general description. We're going to take that from our spreadsheet. We're doing it's a helical boring bar. Just means the boring bar head is a helix. The vendor was Scientific Cutting Tools. Yeah, Scientific Cutting Tools. And we're going to go back and put in our product ID. It's going to be the URL to where we buy it from. Okay, we're going to go to insert. It's not really using an insert, but this is the size of the cutting head itself. Using an insert, but we need to find one that mimics the shape of this. Let's go with a square, since that's as close as we're going to get. And we're going to look at our information. Scientific. Okay, our minimum bore is 0.18 thousandths. Okay, our cutter radius. And now we're going to go to the holder to try to fake the rest of this. 180 thousandths. Our head height. Our shank width, since it's a round shank, it's a lot smaller than what we got there. Our shank is, diameter is 3/16. The overall length of our tool is 2.5 inches. Okay, so we're mocking up this boring bar the best we can. This is a tool is actually set up for inserts, so we want the cutting width to be on center line. What's going to really happen is we're going to set the tool on this corner, and it's going to follow the profile in the program. One thing I see on the shank is it's not allowing us to have a straight cylindrical shank like our real cutter has. So it's going to appear as if it's gouging when it goes into the hole. Okay. So we're going to go to setup, and our orientation, yeah, is going to be facing the rotation in an actual radial way. So, and our feeds and speeds, again, we're going to go to constant feeds and speeds, and I think we're going to increase the surface footage. No, we're going to leave it right where it is. Okay, and 1 inch is about the biggest diameter we're going to do with this cutter, so we'll just leave it at that, and we'll hit OK. And now